So we're going to talk about work. I already said this yesterday, but work is the method by which you change something's energy. That's what we talked about yesterday, the method by which you change something's energy. And it's an overarching topic. So anytime you're changing something's energy, you can be doing work to it. Now, we do know that there's different kinds of energy out there. And I think we kind of glossed over that in this class. But one of the ones we talked about yesterday was what kind of energy? Kinetic. So if we do work, one of the kinds of energies that could be changed could be kinetic energy. And I don't know if we went far enough. Did we talk about how you calculate kinetic energy? Yes. Good. So we know that calculating it is 1/2 mv squared. How to calculate kinetic energy. Does anybody know another type of energy? Talked about it yesterday. Potential. Well, that's not one we talked about yesterday, but I'm happy to throw it down. What kind of energy is potential energy? Maybe we did talk about it yesterday. Stored energy. That's right. So potential energy is stored energy. Now, in chemistry, we would have talked about chemical potential energy, but you probably didn't have a method to calculate it. You might calculate the change in energy due to chemical bonds, but I don't really think you get into that too much in honors chemistry. But there are lots of different. There's chemical potential energy. There's two in this class that we'll talk about. We'll talk about gravitational potential energy. And we'll talk about elastic. And if any of you end up going to E&M, we'll talk about electric. All those are different forms of potential energy. They all share one thing in common, that in order for there to be stored energy, you have to have a system that interacts. A single atom can't store chemical potential energy, but an atom attached to another atom through a chemical bond can. The energy is stored in the bond. A single mass doesn't have gravitational potential energy, but a mass interacting with another mass connected by a gravitational force has gravitational potential energy, and so on and so forth. All of these have to have the interaction between two or more objects in order for there to be stored potential energy. And then one more we talked about yesterday. It was the whole overarching conversation, which was thermal energy. Things have energy because they are hot. Now, we can say that thermal energy is kinetic energy. However, it's hard to see it that way, right? It's hard to see the motion of the particles. And there's so many of them and such. So we sometimes treat it like it's its own thing. But all of them come down to having their energy changed by doing work on the system. Physical work is what we're going to talk about in here, which means physical work is something that is done to the object. And it involves something I think that's pretty straightforward. You have to push on the object. And you have to do so using a force. That's what pushing is, or pulling. So you have to apply a force to the object. That force has to in some way be responsible to causing the object to change its position. Now, it's important to note that there has to be a part of that force in the direction of motion. Now, I'm drawing it this way. I'm not sure I talked about it like this yesterday, did I?
Yeah.
Did we talk about the dot product? Oh, good. So I can advance to being past the dot product. And I want to show you some symbology that needs to be used here. I won't use this most of the time, but in case it comes up, like on another test or something, this is the way that you would write the dot product out. Be careful about what these things mean. These are, you guys have seen these before, right? What are they? They're absolute value. They mean something similar when you put them around the sides of a vector. What you're saying is you want the absolute length of the vector. which means the bars here, you want the magnitude. Remember, that just means size of the vector. So just like the absolute value in algebra, where it just strips off the negative sign if there is one, giving you just the number, this tells you the absolute length of the vector. This is the same. The absolute value bars are just to give us the length of the displacement. But this angle theta, I want to be very careful. We use theta for every type of angle that we have in here, so they mean different things in different contexts. This theta isn't the angle of an incline. I don't even know if there will be an incline in the problem. This theta is the angle between the force and displacement. The angle between the force and the displacement. So what I want to do is I want to do a couple of example questions that show you how we're going to use this. Is that all right? We're going to deal with some relatively easy ones in the beginning. I overestimated what I could expect of third period, so I'm going to start with a slightly simpler example than what I gave them. I'm going to pull a box with a 20 Newton force, and we're going to say the box is 5 kilograms, and we'll say it's on a frictionless surface. Bless you. All right. Let's say that angle is being applied. Let's say the force is being applied at an angle of 30 degrees. Now, due to the action of this force, I think the box is going to move. Is that not unreasonable? Yeah. So, especially with that, there not being friction and the surface being level, I think the box is going to likely move this way. So let's talk about the box sliding 3 meters across the ground, making it to a location over here. Now, when we talk about work, any force acting on the box can do work. How many forces are acting on the box? Can you name one? Gravity. Gravity's acting on the box, so let's go ahead and draw that out. Gravitational force acts on the box. I assume that you would agree that the gravitational force acts downwards on the box. And we kind of know how big this force is because it's a 5 kilogram box. So this must be a 50 Newton force. All good? Name another force acting on the box. Well, I heard two. I heard somebody next to me say applied and then a bunch of you say normal force. I think both of those are realistic. Let's draw in the normal force. I think the normal force is going to act upwards on the box. I don't think it's going to be 50 units long, do you? Because I'm pulling slightly upwards on the box. I don't know how big the normal force is. For that, we would have to do what we did last unit. We would have to do a net force diagram to figure out how big the normal force is. You guys remember that? Good, because I'm going to expect that you could figure out that the normal force here is 40 newtons. Take a moment and prove me right. 60 seconds. Oh, now there's a downward force of 50 newtons, an upward force from the normal force of an unknown amount, and then there's the part of the 20 Newton force that is upwards, which would be 20 times the sine of 30 degrees. Now, in the y direction, I think the net force equals 0. I don't think the box is going to go up or down or accelerate up or down. In fact, if I was trying to draw a coordinate system, I'd probably put my x direction to the right and say that it's net force in the x direction equals ma. But I think the net force in the y direction equals 0. And then I'd probably say normal plus 20 sine 30 minus 50 equals 0. Is that what do you see where I'm going with this?
Yes.
All right, well, 20 sine 30 is 10. 10 minus 50 is negative 40, so normal must equal 40 newtons. You see what I got? Okay. Thank you for asking. Now, the problem that I want you guys to deal with is the work problem. We now know this equals 40 newtons, and every force that acts on the object can do work. So let's remember, work equals the size of the force times the size of the displacement times the cosine of the angle between them. There are 3 forces acting on the box. There's the work done by the 20 newton force. There's the work done by the normal force and the work done by gravity. Let's work them out. Do you notice what I'm doing here? I'm laying out vertically each of the works being done by each force. I'm about to set up a chart, and in that chart I'm going to have force and displacement and the cosine of an angle. So I'm just kind of laying out a chart for me so that I can get all the things down and cover all the forces that are potentially doing work. Now, sometimes, and pretty soon, I hope you'll figure out that maybe we don't have to evaluate them all. But for the time being, we are going to look at every force that acts on the object. Let's start with that 20 newton force. What's the size of the 20 newton force? 20 newtons. Thank you. I know it sounds silly, but I couldn't get that earlier. What's the size of the displacement? 3 meters. The box slides 3 meters. What is the angle between the displacement and the force?
30 degrees.
30 degrees, right? The displacement is in this direction. So the angle will be 30 degrees. So I'll put cosine 30 degrees. Ready to move on? All right, let's go to the next one. What's the size of the normal force?
40 newtons.
So 40 newtons. What's the displacement of the box? What's that? 3 meters. What is the angle between the normal force and the displacement?
90.
90 degrees. Now, is there anybody who need help with any of those numbers? Well, the 90? The normal force points upwards, but the box slides to the right. So I'm actually looking for the angle between those two. Does that make sense? Okay. All right, so let's go to the next one. What is the weight of the box? What's the displacement of the box? What is the angle between the weight and the displacement? It's also 90 degrees. There we go. We have successfully set up a way to calculate the work for each of the forces that's acting on the box. Can you do me a favor and calculate the work on each of the objects? Why don't you tell me one of these?
Okay, I think one of them, the second one, I think is 0.
Why do you think how'd you get 0?
I did my calculator, I did parentheses,
Uh-huh.
40, parentheses, 3, parentheses, and then I did no parentheses, cosine, 90.
And it came out to be 0. What do you think made it 0 and all that? Because 3 times 40 isn't 0. What part of that made it 0?
Cosine 90.
Cosine 90 is 0. That's right. If the force doesn't have any component in the direction of motion, it doesn't do work. So we could look at the picture and know that the normal force isn't causing it to go to the right, is it?
No.
No, and the weight's not causing it to go to the right. I mean, although we wrote all of that out, come on, we probably knew from the very beginning that neither of these forces are doing work if the object's moving sideways. So I want to remind you that although I made you write it out, that any force can do work, it doesn't mean that they all do work. Just the ones that are within the direction of motion. So, no, I'd wipe those two out. We know those are both going to be 0, leaving us with only one. And how much work did it do?
51.96.
So 52 Newton meters. Right? The unit is Newton times meters, which obviously we're going to probably give that a name, aren't we? Did we talk about the name of a Newton meter yesterday?
No.
A Newton meter. Now, pay very close attention because remember when I said the units get weird in here? A Newton meter is actually called the joule, just like you learned in chemistry. Which is why I find it weird you guys use it in chemistry. Because do you see how attached it is to what we do in here? Did you ever measure anything in newtons when you were in chemistry? Was there ever anything in newtons in chemistry? But you use joules for energy? I always thought it was weird. Because do you guys know what the definition of 1 little c calorie is? Not that it's 4.19 joules. What's the definition? Like, where does it come from? I mean, I'm telling you right now, a joule is 1 Newton that moves an object a meter. That's a joule. What is a calorie? And I know you want to say 4.19 joules. That's not what I want you to say. A calorie is defined. Like, this is what I want you to know. The calorie is defined as the amount of energy required to change 1 gram of water 1 degree Celsius. That's a calorie. Do you see why I think you should use that in chemistry? Because how much of the stuff in chemistry is about changing temperature? Like all of it? So using calories in chemistry makes a lot of sense to me. But yes, a joule is a Newton meter. Pay attention. A Newton is kilograms meters per second squared times meter. Do the math on this. That's a kilogram meter squared per second squared, right? Kilogram is a measure of what? Mass. Meters per second is a measure of what? And then we square it. Do you see kinetic energy in there? Do you see it? So when you do 1/2 mv squared, you're getting units that are the same as a joule. So this is named for Henry Joule. And he's not taught very much in physics anymore. And he's not really considered a physicist in a traditional sense. He's named for the unit of energy because he discovered the link between thermal energy and mechanical energy. And he did this hundreds of years ago. He took horses, because he had a farm, and he connected them to an apparatus to a set of paddle wheels that he put in a pool of water. So he took this tank of water with these paddles in it, and then he submerged it under the ground to isolate it. Like, there were no thermoses back there. So he had to do this in like his own thermos that he created, and he thought putting it underground would isolate it from the air and stuff. And then he drove the horses, and as he drove the horses, the paddle wheels churned up the water. He was able to show that the energy of the horses was being transferred to the water by raising the water's temperature. And so he is honored with his discovery that thermal energy and mechanical energy are related. And that's why we name it the joule. Now, it is true that there are 4.19 joules for every 1 little c calorie, which makes joule the smallest unit of energy, because it takes 4 of them to get to 1 calorie. Now, looking around this room, just a minute, over here. When the box was drawn across the road, or across the table, 2 of those forces didn't do any work, but 1 of them did, right? There is what I need to impress upon you, something known as net work. The word net here means the same thing it meant before when we talked about force. Net force means adding up all the forces in the system. Net work is adding up all of the work in the system. Net work represents the total work done on the object. In this case, 52 joules of work was done on the object. Please listen very closely and get this into your notes. Most important thing I'm saying today. If net work is done on the object, it will be equal to the change in kinetic energy of the object. If net work is done on the object, it equals the change in kinetic energy of the object. Now what that means here is pretty straightforward, I hope. If the box started from rest, this equals 1/2 mv squared minus 1/2 mv initial squared. Work problems are very good at telling you how fast things are going. They're very good at dealing with velocity. Because if there is net work, there's a change in the velocity. Now let's talk about my knuckle. I can see that we have a whole lot of people who clearly live at the gym. I do not see that. But let's say that maybe I'm wrong. It is cold out today, so it is plausible that those huge muscles are just being obscured by the jackets you're wearing, and that you guys are quite the gym rats. Yes, we'll say that. So, yeah, So, let's say that Aaron hits the gym a lot. What do you think Aaron benches? I'm going, what, 220?
950. 950. 950.
I think 950 might be pushing it.
4 or 5.
What do you bench there, Aaron? I don't know. Never done it before? The bar is 45 by itself, 45 pounds. A plate is 45. Let's say that we'll give her the benefit of the doubt. Do you think she can bench a bar and 2 plates? I'm going to say yes. So Erin's going to go to the gym today. She's going to say, look, this is just a little light practice. I'm going to put a bar on the rack and put 2 plates on it. That would be 135 pounds. And she's gonna do just her standard, simple. It's just a Wednesday. Can somebody tell me how many kilograms that is? You just divide that by 2.2. I would do it on my calculator, but I no longer have one.
That's not my fault. That's Leo's fault.
All right, so we're gonna say 61.4 kilograms. Now, we're gonna have to do some intense measurement here, so I'll need some help. Can you stick your arms out? No, bench is this way. All right.
You bench 135.
So,
I
put
do
this
not
right in your shoulder. All right, so make a fist. You're holding the bar. Are you paying attention? 'Cause I need your help. All right, so where is her hands against the meter stick? What number? Like the middle, like where the bar would be? 56. Okay, 56. Just keep that place. Now, you bring the weight to your chest. It won't matter. Just bring your weights to your chest. Okay, where is it now? 15 or 16. So we go from 15 or let's just say 16 to 56. Is that fair? So she does a bench press. She goes from 16 to 56. How far does she lift the weight?
0.4 meters.
All right, 0.4 meters. So, when Erin does a bench press of 135 pounds, she moves the barbell 0.4 meters. Can we see that during this process, Erin does work on the barbell? Is that clear? Now, there's more than one force acting on the barbell. What other force is acting on the barbell? Gravity. So there are 2 forces at play here. There's Erin's pushing force. We'll say the force from Erin. And then there's the weight of the barbell, which is clearly 614 newtons. Right? I just took the barbell multiplied by 10. Right? Do y'all see that? mg. Are you all with me?
Yes.
Now, I assume that you guys who go to the gym understand that when you are doing a bench press, the goal is to move the weight in a controlled and reasonable fashion. So it's supposed to be at a nice constant speed. So I believe the net force on the barbell will be 0 while Erin is lifting it. Does that make sense? Because she's going to be moving it in a controlled manner. So she pushes a little harder at the beginning to get it started, then she just needs to maintain that speed until she reaches the top and locks her elbows. Fair enough? Yes?
Like I was looking at that, and it's like this only works for constant force, so all of our questions that we get will be like in a equals.
Right, we're always going to try and make they're always going to be stated in such a way where the force is constant. So we're talking about Erin's force. So while Erin's pushing the barbell, we're only interested in the part where the barbell is moving at the constant speed. Okay? I'm not saying the barbell can't be accelerated. She could push more. So let's say if she pushes at 650 newtons, then the barbell is going to accelerate. So when she gets here, the barbell's probably got some speed and is going to leave her hands. We probably don't want that. Oh, no. And I know you're huge because you've been working out a lot. So let's figure out how much work is done by Erin and how much work is done by gravity. Okay? Work is what? How do we calculate work? That's right. Force times what? Times displacement times what? Cosine of the angle. All right, so let's talk about Erin. How much force does Erin have to apply for the bar to move at a constant speed? 614, that's right. So Erin pushes with 614 newtons of force. And how far does Erin displace the bar? 0.4 meters. And what is the angle between her pushing force and the displacement? 0. Good job. She pushes up, and the bar goes up, hopefully. I mean, if she pushes up and the bar goes down, we got a problem. Now, she will be pushing up, and the bar will go down when she returns it to her chest, right? But I don't think we're going to include that part of this because the bar is going to go to her chest whether she pushes up or not. Agreed? Just slice her in half when it makes it down there. But we're hoping that doesn't happen. She has a controlled return. But we're just going to talk about the push-up. Now, the gravity is also doing work here. So how much work does gravity do? What's the force of gravity on the bar? 614. How far does the bar travel? 0.4. And what is the angle between the gravitational force and the displacement?
180.
That's right, 180 degrees. Excellent. All right. Could you please take a moment and tell me how much work did Erin do on the bar and how much work did gravity do on the bar? I need to hurry because I only got 7 minutes left and I want to make 2 points. So, go ahead.
245.6.
How much?
Are we using joules?
It is joules.
245.6 joules.
245.6? Can I just write 246 joules? We'll round up. We'll say maybe there was the clips are on the bar, so she's a little extra. That all good? How much work did gravity do then? Negative 246. All right. Are we okay? We're trying to figure out 180 degrees?
Yeah.
Okay, do you have your protractor? Can you pull it out for a minute?
It should be.
All right, I'm just waiting. But I need to hurry because I want to make 2 points. She doesn't have a protractor. Oh, my word.
Leo does. He does.
Whoever get one out first becomes my favorite. All right, you're my
Oh, I got a fancy one.
Scratch is closer.
I have a fancy
All
one.
right, here we go. Aaron pushes this way, right?
Uh-huh.
I'm sorry, no. The bar, the gravity is this way. We're talking about gravity, right? Gravity is this way. And what direction does the bar go?
Down. Oh.
Up. So the bar went up. So what is the angle between down and up?
180.
180. It says it right there on the side of the protractor, but you follow what I'm saying? So although
Like that.
gravity's pulling down, the bar is going this way.
But like, let's say like it was like that, it'd be like 90.
Yeah, that's 90. But I mean, the bar wasn't going this way.
Yeah, but if it's going up, it's always gonna be 180.
Well, if gravity's downwards and the object's going up, then yes, it's always going to be 180.
Okay.
I mean, gravity, and think of it this way.
I'm gonna go down.
Gravity's what's keeping the bar from accelerating upwards.
Yeah.
It's also what's making sure that she has something to press against. Now, I need to make my point. I have 4.5 minutes to do so. So let's try and make my point here first. My first point is simple. Go back to the other example for just a minute. Was it on this page? No. Go back to the other example point. What's the network in this case? 0. That's because the object traveled at a constant speed. Its velocity never changed. Because velocity never changed, the network equals 0. And that tells you something. If an object's velocity doesn't change, the network equals 0. Even if you don't know what forces are acting on it. If the object has a constant speed, the network is 0. Now, one more thing. You guys, this is just for funsies because we have a minute left. There are 4.19 joules in every one. Oh, don't put your stuff away. Aaron did 246 joules of work. How many calories was that? Can you divide that by 4.19 and tell me how many calories that was? $58.8 calories. Now, are those food calories? Or are those just those little c calories? Oh, so if I want food calories, you have to divide that by 1,000, right? Can you divide that by 1,000? 0.0588? Big C calories, right? All right, I have a World's Finest, and there's a lot of you eating them World's Finest chocolate bars. You know how many calories are in a World's Finest chocolate bar?
100?
Oh, there are 270 big C calories in a World's Finest chocolate bar. That's exactly what I want. What's 270 divided by 0.5088 calories? 4,591 reps would be necessary for Aaron to be able to burn off that one candy bar. Now,
I did that with the bar. That's small one. 5,000.
now